So, electromagnetic induction. Well, this is certainly a very interesting subject because electromagnetic induction is the phenomenon which makes electric technology possible. So, electromagnetic induction could be stated in several ways. One way of stating it is when a magnetic field changes in time, there exists an associated electric field. Or another way of describing the phenomenon is a changing magnetic flux has an associated electromotive force. Now, you know, electric fields or electromotive force, voltage, is what we need to create electricity, to create electric current. And the way we create electric current for most of the applications of electricity in our daily lives come from magnetic fields that change in time or changing magnetic flux. Now, here are the field equations. Electromagnetic induction is a purely field effect. So the equations depend only on the electric field and the magnetic field. The field equations make no mention of electric charge or electric currents or anything material at all. It's not really a material process. It's a field process. One way to write the field equations, or the field equation for electromagnetic induction, is that the curl of E is minus dB dt. So when there's a changing magnetic field, changing in time, there'll be an electric field that curls around the change of the magnetic field. You see, this is an equation in which the fields, E for the electric field and B for the magnetic field, depend on both position and time. So the left-hand side here involves spatial derivatives of the electric field, and that's related to time derivatives of the magnetic field. Now, another way that I can write this equation, here it's written as a differential equation involving derivatives of the vector fields. I can also write this as an integral equation. And it says the integral of the electric field around a closed curve. So I have a closed curve C. And the integral of the electric field dot ds, where ds is the arc length. So ds is a little arc length on this curve. So E dot ds would be the component of the electric field tangent to the curve, the tangential component of the electric field. So this quantity is the circulation of E around the closed curve C is equal to the negative rate of change of the integral B dot dA over some surface. So here is some surface bounded by the curve C, and dA means a little area part, a part of the surface, little infinitesimal area element, and it has a direction. The direction is normal to the surface. So here we have the normal component of B integrated over the surface. That's what we call the flux. It's the flux of B through the surface. In other words, it's the amount of magnetic field that flows through the surface. And now we take minus ddt of the flux. That's the negative rate of change, or the rate of decrease of the flux through the surface. Now there's an interesting directionality of electromagnetic induction. The electric field circulates around the change of the magnetic field. So those are two ways we could write the field equations. These are equivalent. In fact, this second equation has to be understood in these terms. C is any closed curve in space. And S is any surface bounded by that closed curve. So it's a very general relation between the directions of E and B. Whereas the differential equation is just a statement which must be true at every point in space, at every time. Now, we usually rewrite this equation in a simple form. The circulation of the electric field around a closed curve is equal to the electromotive force around the curve. It's the voltage change around the curve. And we usually write that as script E for EMF. And that's minus ddt of phi, where this phi is the flux of the magnetic field. So when there's a changing magnetic field, or when there's a changing magnetic flux, there must be an electromotive force, which could be used to drive a current. And that's how we make electricity that we use in everyday life. Now, I hope you've watched the video part 1, which explains the theory behind electromagnetic induction. That was part 1. Now, here's part 2. Some examples. So I'll base these examples on problems that are in the long kappa assignment. So here's one of the problems. There's a uniform magnetic field, uniform in space. It's pointing out towards you, pointing out in the z direction. Here's the xy plane. And suppose B, it's uniform in space, but it's changing in time. It's k hat B0 plus beta 1t. So it points in the z direction, that's the k hat, and it's changing in time linearly with time. That's the term beta 1t. In this field, we have a copper ring, which has a radius A and a resistance R. So let A be the radius of the ring, and let R be the electrical resistance. And then the problem is to calculate the induced current. So the problem is to calculate I as a function of t. So as the magnetic field increases, pointing out towards you, there'll be an induced electric potential, and then because copper is a conductor, an induced electric current. And that's what you're aiming to calculate. So, we're given a magnetic field, k hat B0 plus beta 1t. It's changing in time. So we're going to use Faraday's law. We're going to say that the EMF, or the voltage around the ring, is equal to the rate of decrease of the electric flux. So let's calculate the electric flux. Well, the electric flux is the integral B dot dA. The magnetic flux is the integral B dot dA over the interior of the ring, the disk inside the ring. Now B is B0 plus beta 1t, and that doesn't depend on position, so I can pull that outside the integral. B is in the z direction, dA is perpendicular to the ring, so dA is also in the z direction. So B dot dA will just be B times dA. When I integrate dA, I'll just get the area, because B doesn't depend on position. So I'll get B naught plus B beta 1t times the area, pi a squared. Now the electromotive force is minus d phi dt. So I have here minus the derivative of this with respect to time. Beta 0 times pi a squared doesn't depend on time, so that part drops out. The derivative of beta 1t is just beta 1. So I have minus beta 1 times pi a squared. So there's a constant electromotive force around the ring. And that will drive a constant current. Now, what does the minus sign mean here? Well, that's Lenz's law, and it has to do with the direction of the electromotive force. The magnetic field is increasing in the z direction. The z direction is out towards you. Now, d phi dt will be positive, but the EMF will be negative. Negative means it's pointing away from you. So positive means out towards you. That's the direction of increase of B. But electromotive force opposes the change in the magnetic field. So it will be back in the negative z direction. Well, we don't really have a direction here. We just have the electromotive force. It will be negative. The change in B is out towards you, so the rate of change of phi is positive in the outward direction, negative in the inward direction. That corresponds to clockwise. So a negative charge here means a clockwise direction of the electromotive force. Really, I should say I have a negative counterclockwise EMF. If I use the right-hand rule to relate the direction of B, or really the change of B, that will be outward towards you. By the right-hand rule, that corresponds to a direction around the ring, which is counterclockwise. But it's negative, so it's really clockwise. It's a negative counterclockwise EMF. Now I want to know the current. Well, the current will be the EMF divided by the resistance. It's the voltage around the ring. By Ohm's law, the voltage around the ring divided by the resistance is equal to the current. Now that will be negative beta 1 times the area, pi a squared, divided by the resistance. Negative meaning that it's in the opposite direction from the right-hand rule. So the right-hand rule would correspond to a counterclockwise current. The current will be clockwise. All right, so that would solve the problem. Now let's look at something different. What's the electric field? What's the electric field in this copper ring? There must be an electric field which is driving the current. Well, what is the electric field? Well, we can relate E to the electric field. E, the EMF, is the circulation of the electric field. And by the symmetry of the problem, the direction will be in the phi direction. So if this is x, this is y, then that's the phi direction. It's the counterclockwise direction. And so this will be E phi times 2 pi r. The arc length integrated around the whole ring will just be the circumference, 2 pi r. Or I guess I should call that 2 pi a. So E phi times 2 pi a is minus beta 1 pi a squared. And I can solve for E phi at the radius a. E phi is phi, well, E vector is phi hat E phi. E phi is minus, I guess this should be beta 1, divided by, well, pi divided by 2 pi will be 1/2. And then I have a squared divided by a. R here would be equal to a. Now, I'll leave it as an exercise for you, if you're good at vector calculus, to calculate the curl of E. You know, this would be E phi at the radius a, but obviously I could consider any radius r. And so at an arbitrary radius r, not the radius of the ring, but just some arbitrary radius in the space, actually that would be the cylindrical coordinate rho, the distance from the z-axis in the xy plane. So E phi of rho would be minus beta 1 divided by 2 rho. If I'm at the position of the ring, then rho would be equal to a. But this would be E phi of rho for some arbitrary distance from the center of the ring. And now the exercise is calculate the curl of this vector field. And if you've had a course in advanced calculus, you should be able to calculate the curl and show that it's equal to minus dB dt. So that's the differential form of the field equation. In the first example, we took the magnetic field to be uniform. In this example, we'll take the magnetic field to be coming from the current in a wire. So in this example, we have a wire with current I1 of t. And in fact, we'll take I1 to be I0 times 1 minus e to the minus t over tau. So I1 is given. If I made a little graph of I1, the current in the wire, this wire is on the z-axis, on the x-axis. At t equals 0, it's 0. At t equals infinity, it's I0. So it has a graph that looks sort of like this. Starts out at 0 and then levels off at some value, I0. So we're turning on a current in this long wire. And now, nearby the wire, there's a rectangular loop of wire. And the problem is to calculate the current in this rectangular loop of wire. Let's say the wire here has resistance R. So here's I1. All right, that's I1. What's I in the wire, in the rectangular loop? And we'll give the rectangular loop dimensions. It extends from A to B in the x direction and from C to D in the y direction. There'll be a magnetic field that curls around the current I1. So there'll be a magnetic field in this direction. We could call that B1. It's the magnetic field due to the current I1. Here, where the rectangular loop is, it's pointing out of the page. So I'll represent a vector pointing outward as a little dot. So here's B1. At this point, it's pointing outward. Up here, it's pointing outward. Down here, it's pointing inward. You have to sort of try to visualize this in 3 dimensions. So there's an outward magnetic field. That's in the z direction. So there's a magnetic field at the position of the rectangular loop, which is in the z direction. So in other words, it's B sub z k hat. Now I want to know, what's the current around this rectangular loop? All right, so here's the picture again. I have this current I of t, or I guess I called that I1 of t, in the direction of the x-axis. Then above the x-axis, in other words, displaced in the positive y direction, there's be a magnetic field pointing outward. That gives a flux through this rectangular loop. Let's calculate the flux through the rectangular loop. So flux is the integral B dot dA. B is in the z direction. And dA is perpendicular to the area, so that's also in the z direction. So the flux pointing out in the z direction is the integral B dot dA over the rectangle, over the interior of the rectangle. Over the area inside the rectangle. Now, what's the magnetic field up here? Well, that's something we learned last week. The magnetic field due to a current in a long wire is mu naught I over 2 pi r, or 2 pi rho. R, or rho, is the perpendicular distance from the wire to the point I'm talking about. So if let's put it a different color. If I'm talking at a point here, if I'm considering a little point here, the perpendicular distance from the wire will be y, because this is the y direction. So this little point has a position y. And the magnetic field in the z direction is mu naught I over 2 pi y. Y is the perpendicular direction. Now I should be a little careful. This is I1. Mu naught I1 over 2 pi y k hat. It's pointing outward. All right, so let's calculate the flux. This is the flux out towards u. It's mu naught I1 over 2 pi. dA is dx dy divided by y. Now here x goes from A to B, and y goes from C to D. So we have the integral A to B dx. We have the integral from C to D dy divided by y times mu naught I, this current I, over 2 pi. Well, you can obviously do the integrals. The integral dx will just be b minus a. The integral dy will be the log of d minus the log of c, or that is to say the log of d divided by c, natural log. Now I want to know the induced current. So that'll be the EMF divided by the resistance. And the EMF, by Faraday's law, is minus d phi dt. The time dependence is in this current I1. So when I differentiate I1, I'll get I0 times e to the minus t over tau times 1 over tau by the chain rule. So I'll get the induced current, which will depend on t, time t. It'll have an exponential behavior, because when I differentiate e to the minus t over tau, I'll get e to the minus t over tau back again times minus 1 over tau by the chain rule. There's another minus sign here, so that'll cancel the other minus sign, times I0. So that will give you the induced current. That's the current in this rectangular loop. Now I took the z-axis, the positive z direction, to calculate the flux. But of course the induced current will be negative. A positive flux would correspond to a counterclockwise direction, but the induced current is negative. So the induced current will be, in fact, clockwise because of the minus sign. That's Lenz's law. I've considered two examples where the magnetic field changes in time. But in some problems, the magnetic field is constant in time, but the closed loop that I'm considering is changing in time. You know, Faraday's law has to do with a closed loop C and the flux through C. So you have a flux is the magnetic field. The amount of magnetic field flowing through that closed loop is the flux. Now, Faraday's law occurs when that flux is changing in time. Well, that could all happen in two different ways. That could happen because the magnetic field is changing in time, but the loop is constant in space. So then the amount of field flowing through that loop would be a function of time. But there's another way that phi could depend on time. You could have a constant field and moving this closed curve. So you could have a strong magnetic field here and a weaker magnetic field over here. And what would happen if you pull this circuit or this loop out of the magnetic field? Well, then the flux through the loop will be decreasing because you're pulling it out of the field. So there's less and less field going through the loop. So the flux would then be decreasing. Well, that also produces an EMF. So in some problems, the magnetic field is in fact constant as a function of time, but the closed loop is changing in time because it's moving. Again, Faraday's law applies. The rate of change of the flux, or rather the rate of decrease of the flux, is equal to the EMF around the loop. This is in Bauer and Westphal, section 29.4. And a very good example of this is the design for a generator of AC electricity. That's explained in figure 2919. There's a little group of questions called self-test 29.4. And there's an exercise at the end of the chapter, that's exercise 2943, which has to do with exactly this problem of a generator of AC electricity. Not a realistic, modern engineering design, but just the kind of rudimentary design principle. The design of the simplest and earliest electric generators to be invented. So I recommend that you read section 29.4, which concerns this case where the magnetic field is constant, but the loop is changing. And study figure 2919 and answer the questions in the self-test 29.4 and do exercise 2943. It's a simple exercise, and in fact, the answer's in the back of the book, because in the textbook by Bauer and Westphal, the answers to all the odd-numbered problems are in the back of the book, so you can check whether you've got the right answer. Here's a picture. Let me try to blow this up a little bit. You have a rotating coil of wire. I think this was sort of explained in qualitative terms back in the part 1 of the screencast. A rotating coil of wire, rotating in a magnetic field, creates an EMF around the wire. So if you connected these two ends with some kind of sliding rings, that would be a source of electromotive force. It would be an electromotive voltage difference between the two ends of the coil. So I think this is also explained in part 1 of the screencast, or anyway, it's in this section 29.4 in the textbook. You see, As the coil of wire rotates, the flux of magnetic field through the coil of wire changes in time. The flux is the integral B dot dA. Now B is constant. Let's say it's in the Z direction. Now dA is perpendicular to the coil. So in this configuration, dA at any point in the coil of wire, dA would be up in this direction. But now let the coil rotate by 90 degrees. Then dA would be in the perpendicular direction to B. So if this coil of wire rotates by 90 degrees, the flux through the coil would be 0. There wouldn't be any magnetic field going through the square. The magnetic field would just be going parallel to the square. So as the coil rotates, the amount of flux varies. I have to treat the B and dA as vectors. This is B, say the Z component of B, dA cosine theta. Because the dot product of two vectors is the first vector magnitude times the second vector magnitude times the cosine of the angle between them. So if I come down to some other time, here's where the coil of wire is at an angle perpendicular to the magnetic field, or rather dA is parallel to the magnetic field. But suppose the coil of wire rotates by an amount omega t. So phi is omega t. Omega is the rotation rate, or it's the it'll have units of radians per second. It's the rate of rotation. Well, now dA is perpendicular to the coil. This angle is also omega t. So the flux will be integral B dot dA. It'll just be B times the area times cosine theta. As long as B is constant at all points, always pointing in the upward direction with the same magnitude, when I integrate the area, I'll just get the total area times the cosine of omega t. Now the EMF around the coil is minus d phi dt. So I have to take minus d phi dt of cosine omega t. Well, the derivative of the cosine is minus a sine. The minus sign will cancel the minus sign. The derivative of theta with respect to t is omega. So by the chain rule, the electromotive force around the coil will be B times A times omega sine omega t. You see, I have a sinusoidal potential, voltage. So this is the voltage. And there'll be some period of oscillation, say from one maximum to the next maximum to the next maximum to the next maximum. That's a period which is equal to 2 pi over omega. So you see I have an alternating voltage. Now BA omega sine theta would be the alternating voltage for one single turn of wire. But if I have a coil with n turns of wire, I'll just get n times this voltage. Will be the total voltage around the whole coil, all n turns of the coil. So the alternating voltage will be NBA omega sine omega t. Here's the alternating time dependence. So this is as a function of time. The period is 2 pi over omega, sine omega t as period. Delta t is 2 pi over omega. And this would be the amplitude of oscillation. So you see the voltage would alternate between plus V0 and minus V0. So I'd have here plus V0, the maximum voltage, and down here minus V0. And a sinusoidal variation alternating between plus V0 and minus V0. So V0 would be the amplitude of oscillation. All right, so there's probably the best example of a problem in which the magnetic field is constant, but the flux through the coil is changing because that loop is rotating in space. And that's the elementary design for a generator of AC electricity. And I recommend that you study figure 2919. Actually, this figure shows both an AC generator and also a DC generator. But anyway, most of the electricity that we use in everyday life is alternating current electricity. And why? Well, because somewhere in the electric grid, there's a generator in which a rotating conducting wire or coil of wire in the presence of a magnetic field is generating an alternating voltage So if you connected the ends of this wire to some kind of an appliance, like a motor or a light bulb or something like that, and plug it in the wall, you'll get that alternating voltage, and that'll drive an alternating current through the appliance. Well, here's one more example. This has a coil of wire in a circuit. If there's a single coil of wire, that's called an inductor, and it has a parameter called L, the self-inductance. Now, if you have a problem with multiple coils of wire interacting with each other, that would be an example of a transformer. And a transformer has a quantity called M, the mutual inductance. Mutual inductance is very important in AC circuits, but what I want to consider here is a DC circuit. So I'll have a DC circuit. It'll have a battery, an inductor with self-inductance L, and a resistor. The battery will push a current out of the positive terminal, through the coil of wire, through the inductor, through the resistor, and then back to the negative terminal of the battery. And so you see that's a direct current circuit, because at any point in the circuit, the current always flows in the same direction. So here's a problem. You have a resistor, an inductor, and a battery. Let's suppose that, before I close the switch, there's no current, but suppose I close the switch at time 0. So there'll be a current starting at time 0. And, well, the first question, part A, is to calculate the current as a function of time. Now, I won't work out the problem here in the screencast, but it's in sections 7 and 8 in the textbook. I have just a single loop. So this is a circuit with one loop. I apply Kirchhoff's loop rule. The change in the potential around the loop must be 0. So the change in potential across the battery is V. The change in potential across the inductor is minus L di dt. It's negative because this is an example of Lenz's law. It's an example of electromagnetic induction. So there's a back EMF. As current goes through the inductor, there's a potential in the opposite direction. So it's minus L di dt. And now the change in potential across the resistor is minus IR. And Kirchhoff's loop rule says that the changes in voltage around a loop must be 0. So I have this differential equation. Oops, this should have been L. L di dt. So that's the equation. It uses a property of an inductor, so that's section 7 in the textbook. And now we just have a differential equation to solve. Well, you can see from the nature of the equation, it's going to be an exponential. There's going to be an exponential dependence on time. At time 0, when the circuit is first closed, there'll be some value of current. And after a long time, there'll be a constant current. So the self-inductance, or the back EMF, will be 0. So then we'll just have effectively a battery with a resistor. The current will be the voltage divided by R. So let's say the current starts down here. Well, actually, if I start out with no current, then the initial current will be 0, and it'll come up and level off at the value V over R. It'll approach this point exponentially. Well, okay, I'm not going to work out the solution here, but it's in the book. This problem then asks some questions about energy in this circuit. It's a little bit like the DC circuit with a capacitor. If you remember, in a DC circuit with a capacitor, the capacitor gets charged, and when the capacitor is charged up, it contains energy. It contains electric field energy, because a charged capacitor has separated charge. Between the plus charge and the minus charge, there's an electric field. The electric field has energy. So there's energy inside the capacitor in the form of electric field energy. Well, in the same way here, when there's a current around the coil of wire, it's like a solenoid, there's a magnetic field inside. So as it approaches the asymptotic value of current, you'll have a magnetic field inside the coil of wire. Magnetic field has energy, just like an electric field has energy. So there'll be energy stored in the inductor. And for example, part D of the question is to calculate the field energy in the inductor at some time, T1, some chosen time to calculate everything. The formula for the current is in the book, equation 2929, chapter 29, equation 29. All right, so these have been some example calculations. You should be able to take these and take the equations. I hope you've been taking notes. Take the equations and apply them to the ln kappa assignment for this week.